Today, we're looking at something truly mind-bending. A new material that might just be a key to solving one of the world's biggest problems.
I know, it sounds way too simple to be true, right? But what if the answer is yes? We're about to break down the science behind a new invention that seems to defy the laws of physics to generate absolutely massive amounts of fresh water. So, let's get right into it.
First things first, let's just set the stage. The problem we're trying to solve here isn't a small one. It's a full-blown global crisis.
For billions of people, access to clean, fresh water is just not a guarantee. And as the population grows and our climate changes, the need is becoming more and more urgent. Finding a sustainable, low-cost solution is truly one of the great challenges of our time. Now, for years, one of the most promising ideas has involved using the most powerful energy source we have, the sun. But this method has always had a fundamental speed limit.
The concept itself is beautifully simple. You use some kind of material to absorb sunlight, which heats up salt water and evaporates the H2O, leaving all the salt and other gunk behind. Then you just collect the condensed, pure water vapor. It's a clean, sustainable process.
But here's the catch. Based on the amount of energy the sun actually provides, scientists calculated a hard physical limit. You could only ever hope to produce about 1.47 kilograms of fresh water for every square meter of material every hour. And for years, breaking that barrier has been the absolute holy grail of desalination research.
And that brings us to the hero of our story today. A team of researchers has developed a new material, a kind of super sponge, that doesn't just nudge past that old limit, it completely shatters it. And this is it. It's a hybrid aerogel the researchers call RGP. Just look at this thing. This material is so impossibly light, it can rest on a flower without damaging it. It's a three-dimensional, porous network that is mostly air, with a density of just 12.6 milligrams per cubic centimeter. Just wild. So, how do you make this wonder material? Well, it actually starts with surprisingly common ingredients. You take a polymer called polyvinyl alcohol, or PVA, and turn it into a superabsorbent version. Then, you mix that with graphene oxide, and use a hydrothermal process that basically causes the whole thing to self-assemble into this amazing 3D aerogel structure.
So how does a simple sponge like this not only meet, but completely demolish that theoretical speed limit? Well, the science behind it is fascinating. It turns out it has three key secrets.
First, it's incredibly thirsty. The polymer inside just yanks water up into its structure almost instantly. Second, it activates the water, making it way easier to evaporate. And third, and this is the really wild part, it actually sucks extra energy right out of the surrounding air. So let's talk about this intermediate water, because this is crucial. Inside the RGP's network, water molecules don't bond as tightly as they normally do. They form these weakly bonded, activated clusters. And the result? It takes far less energy to turn them into vapor. In fact, this intermediate water can evaporate 86 times faster than regular free water. 86 times!
And that third secret, pulling heat from the air? This slide illustrates it perfectly. If you look at the infrared images, you can see the top surface heating up from the sun. But look at the sides. The sides of the aerogel actually become cooler than the surrounding air. This temperature difference is the key. It causes the aerogel to passively pull in extra heat energy from the environment, adding it to the energy it's already getting from the sun.
And here is the truly mind-bending result, an energy efficiency of 124.8%. Now wait a second, over 100%? How's that even possible? Well, it's because the system isn't a closed loop. It's not just using solar energy. It's using solar energy plus free energy it harvests from the ambient air. It breaks the old solar-only limit by cleverly pulling in extra power from its surroundings.
So the sponge itself is already a massive breakthrough. But the researchers didn't stop there. They decided to add one more incredibly simple, common element to the mix.
Okay, look at this. On its own, under simulated sunlight, the RGP aerogel hits an evaporation rate of 4.89 kilograms per square meter per hour. That's more than 3 times the old theoretical limit, an incredible achievement all by itself.
But now, watch what happens when you introduce a gentle breeze of about 2.5 meters per second. The rate skyrockets to 16.22. That is over 11 times the old theoretical limit. The wind just whisks away that humid air at the surface, which allows the sponge to evaporate water at its maximum supercharged speed.
This is way more than just a stunning lab result. The team took this system outside to see what it could do in the real world, with real seawater.
Here's the real-world setup. You can see the outdoor test rig with the RGP aerogel in a container of actual seawater and a small fan to simulate that breeze. This is where the rubber really meets the road.
And the results were just staggering. Over a single 8-hour period, 1 square meter of this material produced 156.3 kilograms. That's over 156 liters of fresh water. That is an enormous amount of water from such a small area.
So what does that mean in human terms? That single square meter on a single day can produce enough clean drinking water to meet the daily needs of 50 people. Let that sink in for a second. 50 people.
And the water it produces is exceptionally pure. The amount of salt was reduced by a factor of 10,000, and 99.99% reduction, easily meeting the World Health Organization standards for safe drinking water.
As the researchers themselves put it, this unique combination of factors, the super-fast evaporation, the clever use of environmental energy, and just adding some simple convection, opens the door for generating fresh water on a massive scale.
It leaves us with a final, powerful question. We often imagine that solutions to global crises have to be impossibly complex and expensive. But this research suggests that sometimes, with a bit of brilliant material science, a solution can be as simple as a super thirsty sponge and a little bit of wind.